Good afternoon, friends. Namaskar. Let us start with the gating system, basics of gating system. We will assume that we have got the design of the casting for which we have already designed the rising system. So we have the casting with the rising system designed along with the casting, which we have done. Now the casting with the riser becomes our new casting for which we have to design the gating system. Is that clear? We will assume that we have the casting drawing with us for which we have designed the risering system, and we have the casting with the risers available to us. The casting with the risers is a new casting for which we have to design the gating system. Now let's look at this figure on the left-hand side. You'll see the ladle in which there's liquid metal. The liquid metal goes over the pouring lip of the ladle and falls into the basin, which is the pouring basin, and goes down the sprue, which is in the mold. The pouring basin may be on the top of the mold or maybe in the mold itself. The metal goes down the sprue, and below the sprue, you will see the sprue basin. Now, that sprue basin design is very important in the sense that it should be flat at the bottom so that when the metal falls on it, the metal does not undergo much turbulence. If the bottom of this sprue basin is made rounded or hemispherical, then the metal will be very turbulent. So if we have to avoid turbulence, we must ensure that the bottom of the sprue basin is flat with radius to make sure there is no sand erosion when we are pouring the metal into the gating system. From the pouring sprue basin, the metal enters the runner, which is in the case of pressurized system, the runner is in the cope, just above the parting line. You can see on the right-hand side the parting line, cope and drag. The cope is in the top, drag is the bottom. And from the runner, we have got the ingate, which delivers the metal from the ladle into the casting cavity. In the casting cavity, we have the casting, and we have got the flow-offs to remove the air entrapped and any gases that may be entrapped over there, and to remove some cold metal, because the first metal which enters the casting, please remember, when you're doing the gating system design, the first metal which enters the gating system must never enter the casting cavity. The first metal, I repeat, that enters the gating system should not enter the casting cavity, because the first metal carries along with it some gases, some slag. As the system is not full, the gating system is not full, it aspirates air, there will be air entrapment, gases, some slag, and if this metal enters the casting, then we are likely to have defects caused by these inclusions in the metal. So the first metal which enters the gating system should remain in the gating system, and only the clean metal should enter the casting cavity. Please make this note. This will be very useful for you solving most of the casting defects. So we have got a ladle, the pouring cup, the pouring basin in the mold or on top of the mold, the sprue in the cope or cope and the drag. Below the sprue, we have the pouring sprue basin. Then the metal is transferred from the sprue basin into the runner through a overlap. If you want, you can place a filter in the running system to remove the slag. But remember, the slag is liquid slag. It is mixed with the liquid. So liquid slag will not be entrapped by the filter. It will pass through the filter. It is like sugar dissolved in a cup of tea. If you put a filter, it will not remove the sugar because the sugar is dissolved in the cup of tea. So is the liquid slag, which is dissolved in the cup of in the metal, which will not be removed by the filter. I am not in favor of using filters, honestly. I like to make the casting without the filters and with a properly designed gating system. Okay. And just a precautionary note, some filters, they break during transportation, they are covered with coating, and the coating breaks, and it is likely that some of these coating particles may enter the casting cavity. And these are very, very, very hard particles. So they will cause problems during the machining of the casting. So while using filters, make sure that the filters don't have any loose particles inside their holes. Okay? So you can keep the filter if you wish in the runner, and there's an ingate which delivers the metal into the casting, and the cold metal and the air is removed from strategic positions to remove the air entrapment, gases, and any slag. Hopefully, there should not be any slag, and to remove the sand from the casting, which may be entering along with the metal. We come to the figure in the middle. Again, have the mold with the pouring basin on the top. There's a vertical screw, the screw basin, and the runner, and there is a ingate, which we have called the choke. In the case the choke is at the ingate, we call such a system a pressurized system. Choke is that element of the gating system which has the smallest area. It chokes the metal so that the metal behind the choke fills up the gating system. So if we have to fill up the gating system, you must provide a choke. The choke can be at the ingate, or as the next figure, the choke can be at the connection near the screw and the runner. But if you notice, I will tell you something about the choke. The choke should be as far as possible in such a way kept that the running system gets full as soon as possible. As a guideline, if the pouring time for the casting or the mold is X seconds, suppose the pouring time for the mold is X seconds, then the running system should be filled in first 10% of the pouring time. That means in 0.1 second, 0.1x second, the gating system should be full before the metal enters the mold cavity. That means the first metal has not entered the mold cavity. It has only filled up the gating system. You got that point? If you still need any explanation, please let me know at the end of the talk. I will explain to you once again. So it is important to choke the metal and fill up the gating system as soon as possible. If the gating system is not full, imagine water coming out from the tap. When you open the tap, the water stream comes out, and at the top of the tap, where the water is leaving the tap, the diameter of the stream is the inside diameter of the tap. As the stream goes down, its diameter decreases. Same thing happens inside the screw. As the metal leaves the pouring cup basin opening, it becomes narrower. And there's air between the metal and the screw and the metal, and there's a aspiration, there's a vacuum, like a low pressure over there. And therefore, the air from the outside and from the mold is sucked into the screw, and there's air entrapment between the metal and the screw gap where the pressure is low. This air enters into the metal, and that should be kept out of the cavity. Then the metal will go into the pouring basin, fill up the pouring basin, and then into the runner. As the runner is filling up, some metal will start moving from the choke into the mold cavity. So this is one of the disadvantages of this system, where the choke is at the ingate. Before the runner is full, the metal starts moving into the casting cavity. So just be aware of this problem with this choke, with this system where the choke is at the ingate. The other system is you pour the metal into the pouring basin, figure on the right. You pour the metal into the pouring basin. The metal flows down the screw into the screw basin. From the screw basin, it is getting choked, and therefore the screw and the screw basin and the pouring cup gets full. And then the metal starts moving to the tapered runner. In this case, the runner is in the drag. So the runner gets completely full before the metal starts entering the ingates, which are located on the top of the runner. So in this system, there is no metal flowing into the casting unless the whole gating system is full. I normally prefer this gating system, which is known as the non-pressurized gating system, because the choke is at the screw. They also call it screw runner system, and the first one is known as gate runner system. The choke is at the gate runner system. And the second one, the choke is at the screw runner system. Okay? Here you see the down screw. The circle is a down screw cross-sectional area connected to the runner. The runner has got an extension on the right, which is tapered. You can see in the elevation at the down screw with the runner at the screw basin. The runner has got a taper at the end, because the first metal which goes will be caught in the runner end. And then you have got the two ingates from where the metal will be entering the mold cavity. Now, to find out the choke, we said in this system, the choke is at the ingates. So the chokes are A1 and A2. Okay, so the choke in this gating system is A1 plus A2. Now you just go on the top. I've given you the design of the gate section, the gate section should be square. The height of the gate is, suppose A, then the width of the gate should be 4 times the height, 4A. Just keep this in mind. And you can examine the gating systems in your various patterns on your foundry to see whether this relationship is maintained. So you have a gate with a height about dimension A and the width is 4A. So this is important point to remember. And in this system, the choke is A1 plus A2 is the choke. So in all the gating system designs, we will see we have to calculate the choke area first. So we will be talking about the choke very often in today's talk. So this figure on the left-hand side shows you the gating system for the casting. It can have 1 in-gate or 2 in-gates, or it can have more in-gates. So this one has got 2 in-gates. Now, this system is feeding metal to one casting. In another case, you got multiple castings. You got 4 castings. So here you have got the sprue in the middle of the runner on the left-hand side, runner on the right-hand side. On the left-hand runner, you have got 2 casting cavities, one with in-gate A1, and on the right-hand side, you got the second casting cavity with in-gate A2. On the top, you have got third casting cavity with in-gate A3. And on the left-hand side, you got the fourth casting cavity with the in-gate A4. So in this case, there are 2 runners, 4 castings. Each casting has got the choke. So we look at the total choke. You look at the runner bar, there are 2 halves of the runner bar. One on the left-hand side of the sprue and one on the right-hand side of it. Let's say the choke on the left-hand side is AC1. The total choke on the runner on the left-hand side, AC1, is equal to runner in-gate A1 and in-gate A4. So AC1, choke area, total area is A1 area and A4 area. So similarly, the choke on the right-hand side of the runner, on the right-hand runner is AC2, which consists of the total area of in-gate A2 and in-gate A3. So the choke area on the right runner is AC2, which is A2 area and A3 area. You can see here in the elevation, down sprue bottom, runner on the left, runner on the right. A1 is the in-gate on the runner on the left, and on the other side is other cavity. So in-gate is A4. On the right-hand side, you've got the second cavity, in-gate is A2. On the back of this is A3 and the third cavity. So this is a typical gating system for one cavity and multi-cavity patterns. Running system and gating ratios for SG and DIN. So here you have got the sprue cup, circular one, down sprue, and over here they have shown the sprue basin as rounded basin. You can use a rounded basin if you want to put the inoculant in the gating system. But as a late inoculation, when you want to have late inoculation or mold inoculation, you can put loose inoculation of size 0.2, 0.3 millimeters over 0.5, 0.6 millimeters. The granular inoculant can be placed at the bottom of the sprue in the sprue basin. In that case, you can have a circular sprue basin, because the flat surface will be formed by the loose inoculant which you will be putting there, so which will avoid any turbulence. So you have got the parting line, you have got the down sprue, you got the sprue basin, then the metal from the sprue basin enters the runner in the drag, which is runner R1, and then from the runner R1, there is an overlap into the runner which is now located in the cope. Runner R2, runner R3, runner R4. That means there are 3 runners in the cope, and there is one runner in the drag. So the runner in the drag will deliver all the metal through the overlap, which is between the runner R1 and runner R2, into the runner on the cope, and from the cope, the metal will go into the in-gates A1, A2, A3. So A1 is the in-gate on runner R2, A2 is the in-gate on runner R3, and A3 is the in-gate on runner R4. To find out the areas of these various runners, the runner R4 we have the gating ratios given on the right hand side. The spool is known as S or indicated as S. Runner 1, primary runner, which is in the drag. Secondary runner R2 in the cope. Ingates are total ingates. The total number of ingates on the runner or the total ingates. And L is the overlap from which the metal is entering from the primary runner into the secondary runner. So 5, 4, 8, 3 are the ratios in which the cross-sectional areas of these elements are designed and calculated. In the pressurized system, you have got the sprue area as 5, R1 as 4, R2 as 8, total ingate area is 3, overlap is 4. This is the pressurized gating system used for SGIN. Written on the right hand side, pressurized system used for SGIN. In this ratio, 5:4:8, this is 3:4. The smallest number is 3, and the 3 is in the total ingate area. In the pressurized system, the choke is at the ingates. Therefore, the choke has the smallest area, and the ingates have the smallest area amongst all the other elements of the gating system in the pressurized system. If you want to find out the runner area is of the fourth runner R4 is 8/3 multiplied by the ingate area A3. So the runner area is available by multiplying these ratios with the ingate area. So R4 runner area is equal to the ingate area on that runner multiplied by 8/3. Is that clear? Runner A4 area determined by multiplying the ingate on that runner. A3 is the ingate on runner A4. Multiplying it by 8/3 because that's the ratio in which the runner and ingates are designed. Now let's come to runner R3. R3 has got connected to runner R4 and it has got two ingates ahead of it. So area of the ingate A2 and area of the ingate A3. So if you want to find out the area of the runner AR3, it is equal to 8/3, the ratio in which runner and ingate areas are designed, multiplied by all the chokes ahead of R3. So the chokes ahead of R2 and R3 is A2 and A3. So runner area R3 is 8/3 multiplied by the chokes on that thing, which is A2 plus A3. Is that clear? So the runner area is determined by 8/3 multiplied by all the chokes which are ahead of that runner and of that runner. Now let's come to runner R2. R2 is connected to R3 and R4, and there are three ingates ahead of runner R2. R2 has got A1, R3 has got A2, R4 has got A3. So the area of the runner R2 is equal to 8/3 multiplied by the total chokes on this runner R2, which is A1 plus A2 plus A3. So once we design the runner and the ingates, we have got a runner design ready. We have got the R1, which we will talk about in the ratio of half of R2 area, runner area R1. Look at A. 5 is the sprue area, 4 is the R1 area, 8, which is double of 4, is the R2 area, 3, which is a choke, is the smallest area in the ingates, and L, the lap, is equal to the runner 1 area. So the lap is always equal to the runner 1 area. At the end of the runner, if you have to keep the ingate, make sure that the last ingate is at least 100 millimeters before the end of the runner bar, because the first metal which goes into the runner carries slag along with it. The slag will be ahead of the metal. So if you put the ingate near the end of the runner bar, the slag will enter the metal mold cavity. So if you want to prevent the first slag which goes along with the metal from entering the mold cavity, the last ingate on the runner bar should be located at least 100 millimeters before the end of the runner bar. Okay? I repeat, just to prevent the slag which goes along with the first metal and to make sure the runner bar is full before the first metal enters the casting area, the last ingate should be placed at least 100 millimeters before the end of the runner bar, so that the slag is entrapped in that slanted portion or the curved portion and not goes into the casting cavity. In the equation B is a pressurized system for a in gray cast iron. The only difference is screw remains the same as 5, runner 1 remains as 4, but the runner 2, secondary runner is smaller in height as compared to the runner in SG because SG has got more slag. We made the runner taller to make more room for the slag to separate out in the runner. In gray iron, we don't have so much of slag. So the runner in the gray iron is somewhat lesser in height as compared to the runners designed for the SG iron. The ingot is still the same as a choke and is a pressurized system. So the overlap is equal to the area of the primary runner. So the difference in pressurized system for SG iron and the pressurized system of gray iron is the SG iron runners are taller as compared to the runners in the gray iron case. Okay. The last two equation C is meant for non-pressurized system. In non-pressurized system, the choke is at the sprue. So the smallest figure 1 is near the sprue, the runner R1. So R1 is the choke in the case of non-pressurized system. Or you can put the choke the way we showed you in the previous slide. So in the pressurized system, the choke is at the ingate. In the non-pressurized system, the choke is near the sprue. Keep this in mind. And I always recommend people to use the non-pressurized system for the simple reason that in the pressurized system, the gating system does not get full before the metal starts entering the casting cavity. And in the pressurized system, to avoid this problem, we use a non-pressurized system where the gate gets completely full. The gating system gets completely full before the metal enters the mold cavity through the ingates which are located on the top of the runners. These are the two things you must remember very, very, very carefully. These are the reasons why we have a defect. Let's look at the bad line. You will see there's a parting line shown there. The runner is shown in the cope. The ingate is shown where the metal is coming out in the drag. Now, when there is such a case arises, where the ingate has to be in the drag, such a case arises when the entire casting is in the drag. Then you have to put the ingate in the drag to feed the casting with the metal. Now, if you have to put the ingate in the drag for the casting and the runner is in a cope, then as the metal enters the runner, the metal flow is disturbed. At the ingate, which is below the runner base, the metal direction changes. And whenever the metal direction changes, there is turbulence created. And again, when it leaves the ingate, again the metal direction changes. When it comes back to the runner, again there is turbulence over there. So when you have this turbulence causes disturbance, air entrapment, slag generation, sand inclusions, and these particles of sand or air entrapment or gas are likely to enter the mold, the casting cavity. So in this design is a bad design in which the runner is in the cope and the ingate is in drag. If you have to place the runner in the if you have to place the ingate in the drag because the casting in the drag, then you must provide a part of the runner in the drag also, whose thickness is equal to the height of the ingate. You put the runner in the drag also, a part of the runner in the drag, which is as thick as the height of the ingate. So the way to remember is that in a pressurized system, the bottom surface of the ingate and the bottom surface of the runner bar should be in the same plane. See, in the figure 26, the bottom surface of the ingate is below the bottom surface of the runner bar. This causes high turbulence when the ingate is in a drag and the runner in the cope. The bottom surfaces of the ingate and runner are not in the same plane. So this is one mistake most people sometimes do, and they end up with some defect in the casting which they are not able to eliminate. So if you have to use the ingate in the drag, then the part of the runner should also be in the drag along with the ingate, so that the bottom surface of the ingate and the bottom surface of the runner are in the same place, same plane, so that when the metal flows, there is no disturbance to the. Is that clear? So this is figure design is shown in figure 27. The ingate is still in the drag, but the runner extension had been added to a drag so that the bottom surface of the ingate and the bottom surface of the runner bar are in the same plane. Now there is one more point which is important to remember. You see, at the other end of the ingate, the first ingate, the metal will be having a lot of momentum as it is flowing from the down screw into the runner bar. So it has got high speed, high force. So it is likely to erode some sand from the corner of the junction of the ingate and the runner bar. So there will be a corner over there from where the metal will flow and the force of the metal is likely to erode some sand. So to prevent the sand from entering the metal or going into the casting cavity, we provide a liberal radius at the junction of the ingate and the runner bar. Do you see the R in figure 27? R is a radius provided so that sand does not get broken off by the force of the liquid metal, which is coming down the down screw with a high velocity, a high momentum, which is likely to remove some sand particles from the mold. So there, to avoid the sand getting loose, we provide a radius on the end of the ingate, which is away from the upstream of the metal stream of the ingate. You put a radius to ensure that the sand is not eroded from the corner of the runner bar. You must do this for all the ingates. Now look at figure 28. Metal flow, bottom surface of the ingate and the bottom surface of the runner bar, same plane. This is a correct ingate design. Look at the cross-sectional area. The bottom surface of the ingate and the bottom surface of the runner bar are in the same plane, view Y2. Is that clear? So this design gives you low turbulence, ingate in the cope. If you have to put a runner ingate in the drag, then you must also put a part of the runner in the drag whose thickness is equal to the height of the ingate. Bottom surface of the runner and ingate should be in the same plane. That's most important. Now we'll talk about a ferrostatic head. In figure 1 is side ingate. The whole casting is in the cope and the drag. There's a pouring cup, sprue. From the top of the sprue, from the top of the pouring cup to the bottom of the runner, which we call the height of the sprue. The height of the sprue is the length of the sprue from the top of the pouring basin to the bottom of the runner bar. So that is height of the sprue, HSP, height of the sprue. The ferrostatic head. The ferrostatic head is the height of the metal from the top of the pouring basin to the top of the runner bar. That's the ferrostatic head, or the height of the ferrostatic pressure. Now B is a part of the casting above the parting line, and C is the total height of the casting. So ferrostatic head is from the top of the metal surface in the basin to the top of the runner bar. Sprue height is the height of the sprue from the top of the metal surface in the pouring basin to the bottom of the runner bar. B is the height of the casting in the cope, and C is the total height of the casting in the mold. The same thing is shown in figure 2, where the whole casting is in the drag. So height of the sprue is still top of the pouring basin to the end of the sprue, and the height of the ferrostatic head is equal to the height of the sprue. In the bottom grating, again, the ferrostatic head is from the top of the pouring basin to the parting line, where you have the casting is between the cope and the drag, and the height of the sprue is from the top of the pouring basin to the bottom of the runner bar, which is in the drag. In this case, the whole casting is in a cope or drag, so C is equal to B. The part above the parting line is in the cope, and C is the total height of the casting in the cope. Now the equation for finding the ferrostatic head. Ferrostatic head is equal to HST, ferrostatic height, is height of the sprue minus B squared divided by 2C. B is the part of the casting above the parting line, and C is the total height of the casting in the mold. The velocity of metal flow in the ingate will be the velocity of the metal flow.
The velocity of metal flow at ingate is equal to square root of 2G into HSP minus B square upon 2C.
These are the two types of gating system. The first one I just showed you is a wrong gating system, because the runner is in the cope and the ingate is in the drag, and the bottom surface of the runner and ingate are not in the same plane. So this is the wrong design of the runner and the ingate. The one in the middle is right. The bottom surface of the ingate and the bottom surface of the runner are in the same plane. And the one to the right is also right, because the bottom surface of the runners and the bottom surface of the gate are in the same plane. This is the required of the junction in the gate runner system or a pressurized system. The figure on the right hand side is the design, right and wrong design for a non-pressurized system. The runner on the right hand side is in the drag, and the ingate is connected to the top of the runner. Now, in this case, as the runner is filling up, the slag will be accumulating on the top of the metal surface on the runner bar. This slag will enter the gate and enter the mold cavity. So if the ingate is located at the top of the runner bar at the parting line, then the slag will enter the mold cavity. The right way is to put the runner ingate on top of the runner bar, not at the top of the runner bar, on top of the runner bar. So that once the runner bar is full, the slag is on the top, only a small amount of metal is entering the ingate from the small opening overlap, from where the slag will not be able to enter the metal going into the casting cavity. So in the case of a pressurized system, the bottom surface of the gate and the bottom surface of the runner bar should be in the same plane. In the case of the non-pressurized system, the bottom surface of the gate and the top surface of the runner bar should be in the same plane. Have you noticed this? The bottom surface of the gate in the non-pressurized system and the top surface of the runner bar should be in the same plane. In the right hand side, the bottom surface of the gate is below the top surface of the runner bar. That's why it's a wrong design. The metal with the slag, air, sand will be entering into the casting if you use a wrong gating system in the non-pressurized system. When you're making a layout of the casting of the pattern, keep these points in mind. You must have optimum space utilization for casting. The casting means casting and the risers. Chosen risering method is used for the castings. Parting to minimize need for cores. Make the parting such that you need less cores, and you can use less space for the cores. Then the filling of the metal in the mold cavity must be quiet filling, no turbulence and gas entrapment. The gating system should be simple and symmetrical. Identical gating and risering for identical castings. The risering you have already done for the casting. So the gating for a identical casting should be identical. Use of one riser or more, then one casting if possible, that will increase the yield. Use of one riser or more for one casting, then one casting is possible. Space must be available for adequate gating and risering. The first metal that enters the gating system should not enter the casting cavity. This I keep on repeating because this is the most common mistakes which I've seen in most foundries. Selection of the gating system. In the gate runner or pressurized system, castings are choked individually by one or more chokes at the gate. With the screw runner system, it is possible for several castings to share a common choke. So the choke is near the screw. Use the non-pressurized system for large number of small castings in one mold where it is impractical to choke the casting individually. When you got large number of castings, use a non-pressurized system. Use a pressurized system for other castings. Step-by-step design of the gating system. On receiving a component drawing, the methoding work should be carried out step by step. Step 1 is to contemplate and visualize the casting. Study the component drawing. Mark out the casting drawing by adding machining allowances, deleting small machined holes, and noting the resting points and the location points for the first machining operation. Try to visualize the casting in the isometric view for easy understanding. Step 2 is to draw preliminary mold scheme. Mold scheme means the plan in which you want to make the casting with the location of the cores, the location of the risers or feeders, the location of the ingates, the distance between the casting and the gating system. So steps to be taken now in preliminary drawing. Draw the parting line on the casting drawing. Place the heavy portion of the casting in the drag. Place the heavy portion of the casting in the drag and the thickest portion section of the casting near the parting line, because we will be putting the feeders at the parting line. So when you put the thickest section of the casting at the parting line, it is easy to feed the casting section, thickest section, and heavier section in the drag. So the feeder will be feeding the thicker section, and the thicker section will be feeding the heavy section. Point number 2, mark out the position of the various cores, position of the ingate connections, position of the vents to remove the cold metal, to remove the sand, to increase the slag, to remove the slag, to vent out the gases, position of the feeders, and position of cold metal flow-offs, because the first metal which enters the mold cavity is cold. So we must remove this first metal which is cold, otherwise we will have cold metal defects in the casting. So we provide cold metal flow-offs to remove the first cold metal that may be in the casting. Away from the gating system is normally where the first cold metal will be reaching. So you put the cold metal flow-offs at the end of the opposite side of the gating system. We are only talking about the calculated feeder size, which is already done. We'll be doing this feeder design in the next episode. But calculate the feeder size, calculate the weight of the casting, calculate the feed metal requirement of the casting of the castings using the formula. Feed metal requirement is about 5% of the weight of the casting. The casting consisting of casting plus the feeder. Casting plus feeder is a new casting for which you are designing the feed metal requirement. The feed metal requirement will be the feed metal requirement of the weight of the casting. The casting being the casting plus the feeder. The feed metal requirement demand because of the shrinkage of the metal during solidification and dilation of the mold. The mold gets bigger on putting in liquid metal. Even if it is made in high pressure molding, the mold and mold dilation and shrinkage of the casting is about 4 to 5%. So the feed metal requirement is about 5% of the casting weight. Calculate the feeder size. Calculate the modulus of the casting. Locate the significant sector of the thickest dimensional section. Calculate the modulus of this casting by simulating to the simple geometrical shape. We'll talk about this in the feeder design episode. Just remember that they calculate the modulus of the casting. How to calculate the modulus of the casting, we will see in the next episode. Then calculate the feeder modulus. The feeder modulus is 1.1 times the casting modulus. The feeder modulus is bigger than the casting modulus, so that it has got sufficient feed metal to feed the casting shrinkage over 4 to 5%. Calculate the feedable output of this feeder considering this efficiency. We'll speak about this thing when we talk about the risers and feeders. The feedable output of the feeder must be more than the feed metal demand of the casting. If it is less, more number of feeders are required till their total output is more than the feed metal requirement. This is simple logic. Now, we have given tables. A larger feeder can also be chosen that meets the feed metal requirement without calculating the modulus of the casting. If you choose a large feeder, you'll be able to get the feed metal requirement from that feeder for the casting, even if you don't have the modulus of the casting. Because I told you, the feeder modulus is 1.1 times the casting modulus. If the shape of the casting is such that there are got large sections, middle sections, thin sections, thick sections, all types of sections, then we have to provide feeder on each of the sections, because the feeder should be connected to a section which is smaller than that section. That section should be connected to another section which is smaller than that section, so that the smallest section is at the end of the feeder. But if that is not the case, and there are larger sections in the middle of the casting, then we must provide a feeder for that last section in the middle. That means where the casting has got different section thicknesses, then a feeder has to be connected to each of the thick section casting. Each of the thick sections of the casting. Such feeders should have greater modulus than its own, and that the total feedable output of this feeder should be more than that of the feed metal of the demand of the casting. Maximum feeder utilization can be achieved by feeding 2 or more castings by one feeder. This is common sense. Consider this for feeder calculations and attempt it in the drawing and layout of draw the layout and draw the skeleton of the running system. Attempt to place a maximum number of pattern cavities or casting impressions on the pattern plate. Leave a minimum of 50 mm sand wall between the pattern cavity and the mold box. Otherwise, the sand will be loose or loosely compacted between the pattern and the wall and will become inclusion in the casting. Leave adequate room for gating and rising systems. Avoid angular placement of the pattern cavities. The layout should be possibly symmetrical to the center line of the pattern. Draw the layout and skeleton gating system. Ensure that each pattern cavity is identically gated and rises. Make your job easy cut paper pieces of the size of the pattern cavity at the parting line and place them within the borderline of the pattern plate drawing. The best various combinations is then selected for drawing a layout. Step 5 is to calculate the running system. First, we have to find out the pouring time. Determine the pouring time. We are giving you two curves on slides 34 and 35 below. We'll go there. Yeah, you can determine the pouring time or the choke area from these two curves. One is the metric. So we determine the pouring time. If you don't have the curve readily available, you can approximate the pouring time as pouring time in seconds is equal to 0.9 times square root of 2g, where g is the weight of the casting, weight of the gating system, and weight of the risers, all in kg. So this is one we are getting approximate pouring time of the mold. Then calculate the effective peristaltic head. The peristaltic head is equal to HP minus B square upon 2C. And we have put this under square root to get the velocity of the metal. We have given the formula for the choke area. This is the important formula which you have to use in calculating the choke area. The first thing we have to do is the choke area. The choke area is equal to 22.6 multiplied by G, which is the total weight of the casting or the metal in the mold, divided by rho, which is the density of liquid metal. For SG iron and gray iron, you can use a figure of 6.8 grams per centimeter cube or 6.8 kg for decimeter cube. Zeta is the velocity factor, which is a friction loss factor. The friction loss factor here is between 0.4 and 0.6, but assume 0.4 because in the sand surface is quite rough. So metal loses the velocity because it moves on the rough surface. So use a friction loss factor as G is the weight of the liquid metal per mole in kg. T is the pouring time and HT is the ferrostatic head. We have discussed all these individual parameters earlier. Calculate the screw area, primary area and secondary area gating ratio. The gating ratio I told you in the second slide, area is a relationship between the area of the choke, the area of the runners and the area of the ingates. So the screw area is 5, the runner area is 4, the primary runner area is 4, the secondary runner area is 8 in the SG iron, and secondary runner area is 6 times of the 1.5 times the height of the runner 1, and choke is still A3. So this is the last step in the gating system design. Next slide, please. Draw and release the mold skin drawing, layout drawing, and running system drawing for pattern making. Take trials, use chills if required, section the casting produced on trial basis, release the pattern for mass production if castings are free of defects. This is a pouring time chart. Choke cross-sectional area can be obtained from the weight of the metal poured per choke. And this is also the same. Here I've given you, if you have got individual choke areas, you can design the whole gating system from this table. All the parameters which are defined. C is the diameter of the sprue. R, spherical at the bottom of the sprue basin. B is the bottom surface of the primary runner bar. A is the top surface of the primary runner bar. Capital H is the height of the primary runner bar. Inclined slope is 45 degrees. So the overlap has got parallel surfaces. The length of the overlap is equal to, we have seen, L. The height of the secondary runner bar is H1. The top of the secondary runner bar is equal to top of the primary runner bar B. The parting line width is A in both the cases, primary and secondary runner bar. And W is the width of the ingate. So all these parameters, their values are given in the ratio in the table on the right hand side. Total A, total ingate area, 3. Total runner bar area, 6. Total runner bar area, screw area, secondary runner bar, primary runner bar, overlap, and screw diameter. This is also calculation given for SG iron. The previous one for grey cast iron, and the next one for SG iron. Okay, this one has got runner 2 at 8 times. The first one was 6 times. Okay, now we are given the height of the ingate. So A is equal to 4A. Remember, I showed in the first slide, the width was 4A. Remember, first slide, cross-section area of the ingate was A times the height and 4 times the width. Gating system design. When using filters, the design of the runners and gates will be different. volume is reduced because of the filter, since the choke will be at the filter. And ensure the screw does not act as a choke. Design the screw area as per this formula, where capital H is the height of the pouring basin from the parting line, and small h is the height of the metal in the pouring basin. So the square root of the total height of the screw in the screw divided by the height of the metal in the pouring basin, square root multiplied by the choke is the area of the screw cross section. Sum of all the chokes cross sectional area is AC, and AS relates to the smallest cross section area of the screw. If you have a tapered screw as in hand molding, then the smallest cross section area will be at the bottom of the screw. We cannot have a tapered screw in the automatic molding machines because you cannot remove the screw there. If you're using a filter, the filter is kept between the runner on the top and the runner in the bottom, so that it acts like a choke. And the filter design, the filter efficiency, filter metal capacity, flow rate, dimensional accuracy, and strength of the filter should be enough to make sure this doesn't get damaged. And the filter should never be kept at the bottom of the screw. If you keep the filter at the bottom of the screw, the falling metal will damage the filter. The filter will have a hole in it and there will be no filtration. So never keep the filter at the bottom of the screw. The metal should not directly fall on the filter. If the metal falls on the filter, it will make a hole because it will dissolve the metal of the filter. Even though the filter is covered by the ceramic coating, it will just dissolve the metal without any problem, and there will be a hole and the metal will be flowing without the filter. So never keep the filter at the bottom of the down screw.